All right. So yeah, this is 2 lectures in 1. It's the rotational second law, as in Newton's second law, and the rotational momentum lecture. Both of them combined because they were not terribly long. So yeah. And yeah, starting off, second law. What do we know about Newton's second law? We know that it states that F equals ma. Now, we want to make it rotational. We know that much. So the rotational counterpart of force is torque, and that is equal to whatever the rotational counterpart of mass is times, and the rotational counterpart we know is alpha from our previous units. So it brings the question what the rotational counterpart of mass is. And what that is called inertia. And inertia, or the moment of inertia rather, is the quantity representing a body's tendency to resist angular acceleration, kind of like how mass is its ability to resist linear acceleration. The inertia would be the same for rotational. And yeah, what it really is just the sum of the products of the mass, of each particle within a body. So like, say you have a square, it would be the sum of the mass of each particle inside the square that makes up whatever it is, and that multiplied by the squared distance from wherever the point of, or the axis of rotation is. So if it's rotating about a point here, it would be whatever this distance is, whatever this distance is, this distance, dot, 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 If instead you had a square with an axis of rotation in its middle, it would be all the particles, and then this distance, all that good stuff. And yeah, so I equals mass, the thing's mass, times the radius squared, like its radius. Yeah. So that's a general equation for I. Now, it should be noted that there's different objects and shapes have different I's, or rather different, formulas for I's, because they'd be missing certain parts of their mass, because they might have like a hole in them, right? Like a donut, say, or a bagel, that would have a weird mass because it's kind of missing just this inner part. So yeah, a few of the common ones are a cylinder having a mass of 1/2 mv squared, or mv, 1/2 mr squared, right, the radius. You have, trying to think here. Alright, a sphere would have a mass of, is it, I think, 2 or 3? 2, yeah. It's a mass of 2/5, or an I, this is for a sphere, of 2/5 times the mass by radius squared. And a thing, one of those oh god, one of those things where like you'd have like a string coiled around it and then like it moves. A pulley, it's called a pulley. Right. And the moment of inertia of a pulley is also going to be 1/2 mass by radius squared. So yeah, now we know the counterpart of mass, and we know that Newton's second law in rotational, where the rotational length is torque is equal to the moment of inertia times the angular acceleration. So yeah, that's a pretty good starting point. And now we've sort of reached a point where we know the angular counterparts of most all of the translational, you know, jeez, I cannot think today. Translational stuff. What do you call these? Units, labels, like acceleration, mass, force, those kind of translational stuff, and we know all the rotational counterparts of them. So we can really start applying this sort of switch from translational to rotational kind of mindset to most everything we've learned thus far. For example, you know, you already have your kinematics equations. We did that last time where we moved them to be rotational. And we just did F equals ma as well, so Newton's second law. Alright, so as I was saying, we can, now that we've gotten into the mindset of making previously translational, let's call these subject matters like force, mass, acceleration, all that, we can kind of apply that across everything we've learned thus far. So for example, if we wanted to find what rotational work is, you just know that work, not rotational, right, is already force times distance, right? And we know that theta is equal to distance over radius, so distance is equal to radius times theta. Is my brush bigger? I don't know. It's less brushier. And then you can also apply this logic to momentum. Momentum, rotational, which you actually just write as L. I don't know why it's L, but it's L. Is equal to, where you have normal momentum, is just mass times velocity. So again, rotational counterpart of mass, I, rotational counterpart of velocity is omega. So it equals to I omega. You can even kind of, you know, you have torque equals I alpha, and just the same way that you derived momentum equations, where you just divide by seconds, you can do the same here. And you have, or multiply by seconds, sorry, where you have torque times seconds equals I omega, right? Because you just multiply both sides by seconds, because alpha here is omega over seconds. And yeah. Now there's some times where, yeah, I'll like a quick example of applying this rotational second law is, let's say you have a pulley system, right? And this pulley system has two masses hanging from it. Has this mass here, and this mass here. Alright, let's say that this mass is 44 kilograms, and this one is 11. And now that we know rotational what was I saying? Right, now that we know about like torque and stuff, we can also start treating these systems where we take note of the mass of the pulley as well. Whereas before we always just pretended that the pulley has no mass, so we didn't consider it in our equations. Now we know that it does have mass, and now we have the tools to deal with that. So this mass of the pulley here is, let's see, I'm just going to say it's 5 kilograms. We'll see what comes of our work then. Let's pretend that we also notice that the system, as of right now, is accelerating linearly right here at 5 meters per second squared. And let's also say that the radius of the pulley is just 1 meter. Now, how do we take on this problem? Well, our first step is to split it into every portion that has a mass, right? The forces or torques that act on every portion with a mass. So let's start with this block here. We'll call it mass 1. And this will be our second mass. Yeah, so we have the force of this mass is equal to what are we trying to find? Did I give away a few too many things? Alright, let's say we don't actually know the acceleration. So let me just erase it real quick. If we just make this 24. So we don't know the acceleration, and we're trying to find it. Okay, so A equals question mark. We're still using the same strategy, where we just split it up into the 3 separate masses and calculate the forces or torques that act on each mass. So for this first mass, we know that it has a force acting upon it, and this force will be equal to that mass, right, m1, times whatever the acceleration is. And we also know that it's going to be equal to the sum of the forces. Now this box here will only have 2 forces acting upon it, the force of tension 1, like the tension between right here, and it'll have a gravitational force. We don't know which one is bigger as of yet, because we don't know which way it's accelerating. Now we could probably assume that tension will be bigger because of this, but we don't actually know that. So we know that this is equal to tension 1 times plus minus, you know what, let's actually make tension negative, so our positive direction is down. So negative tension plus Fg is just mass times gravity, right? So times m1, or plus m1 times g. Now, I'll try to keep both of these. Hang on, just zoom out a bit. There we go. Oh, now it looks more. No, I digress. So that's our first kind of portion. For our second portion, let's take on this mass here, the second mass. We know that again, the force of this mass is equal to this mass, so m2 times whatever the acceleration is, and these should be the same acceleration, right? So that, and then that is also equal to this tension here, tension 2, which is once again going to be negative because it's going up instead of down, plus, and we said down was positive, so plus Fg here, which is just mg, so times mass 2 by gravity. For the third part, gotta zoom out even more. We know that the torque on this pulley here, it has tension 1 here and tension 2 here. That's all that's acting on this pulley. It's going to be equal to its moment of inertia times its angular acceleration, right? Torque equals I alpha. That's the rotational counterpart of F equals ma. And this is also going to be equal to the sum of the torques. So we'll say T2 is positive, T2 minus T1. Now, we're trying to find acceleration, right? And we know that alpha equals A over R. So let's make this acceleration as well, which means that acceleration equals alpha times R. So let's write again the moment of inertia, which since this is a pulley, we know is going to be 1/2 times the pulley's mass times the radius of the pulley squared. Now that times acceleration times radius, because we just said that alpha is equal, or acceleration is equal, what? Whoa, sorry. Alpha equals acceleration times R. And this is going to be equal to T2 minus T1. Now we're trying to isolate this here variable. So we want to find what T2 and T1 is, right? Because all this other stuff we already know. And that's where these equations come in. First, let's solve for T1. We add T1 to this side and subtract MA from this side, and we have T1 equals mg minus MA. And then we do the same sort of thing here, where we add T2 here and subtract MA here, and we have T2 equals mg minus, this is M2, minus M2A. So now we plug this into this equation. So we have 1/2 times the mass of the pulley times the radius of the pulley squared times the acceleration times the radius is equal to, in parentheses, the second mass times gravity minus the second mass times acceleration, all that minus, this would be mg minus ma, so to simplify it is minus mg plus ma. I hope that made sense, right? That wasn't insanely difficult or anything. It's just going to save us a bit of time here, and I don't have to rewrite this again. So yeah, now we're trying to find acceleration, remember? So we want to isolate our variable. How do we do that? We add this to both sides, so we get this acceleration here, and we subtract this from both sides, so we get that acceleration over there. And we end up with 1/2 times the mass of the pulley times R squared times R is R cubed, so we'll just write it as that. Times A, right, is equal to M2 times A, so plus M2, and now both of these are multiplied by A, right? 1/2 MP R cubed A, M2A, minus MA, so minus M1 times A. And this will be equal to m2g minus mg. So if we divide both sides by this, and we get that A is equal to gravity by m2 minus m, this is in m1, right? All this over 1/2 the mass of the pulley times the radius of the pulley cubed, because all of these radii, oh boy, I will go back to the start here, I am so sorry. Torque is equal to not just forces times the radius, so all this times the radius again and again. Which means that this is actually radius again here and radius again here, and this m2a, which we added over here, would also have a radius, and this ma, which we subtracted over here, would also have a radius. So 1/2, right, and this has a radius. Right, so that 1/2 mpr cubed, that stayed the same, plus the radius by the second mass minus the radius by the first mass. And now we can cancel out, and this 3 would become a 2, all these radiuses. And then we plug in our variables, so it's going to be equal to gravity, 9.8, by the second mass, which is 44 kilograms, minus the first mass, which is 11 kilograms. All of this is over 1/2 by the mass of the pulley, which we said was 5 kilograms, by the radius of the pulley squared, which we said was 1 meter, so 1 squared, plus the second mass, right? Yeah, plus the second mass, so plus 44 minus the first mass, so minus 11. And then if we plug this into the calculator, we get that the acceleration is equal to some number. Let me pull out my calculator here real quick. 9.8 times 33, all of that divided by, oh boy, 0.5 times 5 times 1 squared is 1, plus 33. We get that our acceleration is 9.11 meters per second squared. And that's that. So that's the first lecture. Right? And you see it wasn't very long, because all this right here is just an example problem of us using all that we learned. And the second lecture is even shorter, I think. Was it? Yeah, no, it was. Yeah. Sorry, I knocked my microphone over. So the momentum lecture, or the collisions lecture, if you want to call it that. Let's get to it. We already figured out that the mass, or rotational momentum, is IW, right? We did that up here somewhere. Here it is. Yeah, now we also want to know, because say you have like, I don't know, some sort of question that's like, you have a ball sliding here and then it hits like this cylinder, sphere, cube thing, right? Actually, you know, easier to imagine it as just a beam that will rotate above this point, right? And then that's going to become like, I don't know, say this cube stuck to it. So it's going to become this sphere here, which also has the cube attached to it now, and that's rotating somehow. We can't just say that the rotational momentum is equal to the linear momentum, because they're different things, you know, they exist in different sort of realms, if you will. It's not like, you know, energy, where you have kinetic rotational energy and just normal kinetic energy, and they both end up being joules, so you can just think of them as the same thing, because these would have rotational momentum and normal linear momentum have different, oh my god, I can't remember the word. Units? Yeah, units. So you can't just set them equal to each other like that. Which means that we need to find a way to make our rotational momentum be seen, or make our linear momentum into rotational momentum. So we can take our original equation, L equals IW, and we can split these up to what they really are. L equals mass by radius squared. Alright, split it up into its linear counterparts, times V over R. And now we see that this radius cancels out this square part. And if you want to go between translational and rotational momentum, you have L equals the mass times the velocity times the radius. This radius is kind of like the torque radius. It's just going to be the radius of where this force is acting, or momentum is going to act. So this radius, not the radius of the ball. Which means that if this was a ball moving of mass 5 kilograms, moving at 2 meters per second, and this was a stationary kind of thing, beam, and the radius of this beam was 1 meter, then your initial rotational momentum was equal to 5 times 2 times 1, or 10. You can even calculate what, assuming, obviously, you know, you still have conservation of momentum, just like how conservation of momentum was no external force, or the net external force was 0. For angular momentum, it's the net external torque. So torque net equals 0, and that equals that the momentum was conserved. So we can assume that there were no external torques here, and we can find out what this final rotational speed was. So we have this, and it's going to be equal to I times W. It should be mentioned that this I would sort of be the net I's, because you have both the ball and the beam here. So, right, so it would be the I of the beam, which we can just say that was given to us as I beam equals 2, plus the I of the ball, except this I of the ball is really just the I of this point here, because we're going to treat it as just one point of mass. And that's a certain radius from the x-axis, so it's just going to be mr squared. Right, so we have 10 equals, we said this is 2, so 2 plus the mass of the ball, 5, right, mr squared, times the radius of where it impacted, which we said was 1, times 1 squared. All that times whatever this final rotational speed is. And we know that this is going to be 7, so this final rotational speed will be 10 over 7. Or if you want to write it differently, 1 3/7. And yeah, that was short. That's all there was to the angular momentum. Bye.